Hey, my name is Saeed Bakhshi, and I'm from Tampere University, working for AI in safety critical systems. Most of the things that I want to address here has already been addressed by the other speakers. And this work is a little bit more bringing everything together to just show what problems we face on a practical approach in the machine learning specifically. So the question is it possible to use machine learning in safety critical applications? Third year of my research now, and I can say, yes, it is possible. However, as people mentioned, there is no standard yet. So we have to work around it and find some way to make sure that the system works. And from my point of view, this can be done by letting another system control the overall safety and just use the machine learning as a tool to provide more information instead of just letting it control the entire system. So the first essential step in developing something safe would be listing any potential faults and hazards it might introduce to the system. And here I will provide a list that I gathered might not be the most complete, but it is more complete than the other alternatives that I found at least, and more practical. So we divide the machine learning into 4 phases. The first phase is, I call it data acquisition, which is related to actually all the steps, all the upcoming steps. So we need data. Is it for training? Yes. Is it for testing? Yes. Is it in the inference phase? Yes, we need data. So data can become either severely distorted, like you can just lose the entire data instead of getting anything from the LiDAR sensor. When it's minus 10 degrees, some points get dropped out. That is data loss. Or it can have subtle corruptions, like you can have some noise on your data or motion blur or anything else. And while severe distortions seem more hazardous, actually subtle corruptions tend to destroy the network more often, because severe distortions are easier to catch on early stages, while the corruptions are not that easy. And with the inherent nature of the machine learning, it can learn anything and everything. So it might actually learn the noise as part of your data. Here is an example of how hardware can distort your data. This is several examples of how a faulty camera produces a faulty image. There are some solutions to the faulty hardware at least. So first safety concern is make sure your hardware is perfectly safe. And since hardware is not something specific for machine learning, we have a lot of standards and a lot of regulations already in place. So I just named some of the functional safety standards, ISO 27272 and other examples. And some other methodologies that have been used, like data fusion, classical approaches, shielding, proper use of redundant sensors, and so on and so forth. However, is it enough to actually solve all our problems with the data? No. As I said, we have subtle corruptions. And these are examples of blurry image, motion blur, for example, frosted glass blur, which might appear if there is, let's say, rain and a droplet drops on your camera. This is not a hardware issue anymore. This is an environmental issue. And solving these problems usually requires some adjustments in your algorithm. So there are methods in image processing that can do denoising, deblurring. However, while these methods have proper use, they have some mathematics that you can use to validate them. They are not necessarily foolproof, because let's say, for example, denoising images usually makes it blurry. So you're solving one problem, but you're introducing another problem. So it's safe to assume that all our data will have some corruption in it, and we need to build our models around it and deal with them. So this is our first problem. And whether it's whether we develop better sensors or better methodology of shielding against noise or other environmental issues, or better methods of dealing with them, that's an open question in the research right now. Next step is the training phase. Right now we have the data and we need to train. And as other speakers mentioned, machine learning is data hungry, and there are some requirements for the data. The data, for the training at least, has to completely represent the task. It has to provide samples from all situations, so similar distributions between all situational cases, and the data should be independent from each other. There should be enough samples to train the network, and the samples should be clean of noise, whether in the labels or in the samples themselves. This is impossible. So let's give an example of why this is impossible for the companies. Let's say on the easiest case, a classification example, which is considered to be the basic building block of all the other models. An image, if you want to check the quality of an image to make sure it's good enough and then label it, would take, give or take, 10 seconds. Then you have to spend another 10 seconds to make sure the first guy didn't make any mistake. So that's 20 seconds per image. On average, on a week, you can produce, let's say, 14,000 images this way. You need 200,000 images. That's, give or take, half a year worth of just labeling images. No company is willing to, at least I don't think no company will be willing to pay that amount of money just to gather one data set that might not even be useful. So how do we deal with this problem? So we go each step. So for the completeness of the data, there are methods. You don't have to necessarily use supervised learning. The semi-supervised and unsupervised learning doesn't require labeling or as big a, sorry, this is for the completeness, not the, I'm sorry. So for the completeness, you need to gather data from your task. You need to make sure that your data set represents your task entirely. And this is done by defining your task properly and gathering the data based on the definition, and making sure that all the rare cases that you can think of is represented in the dataset. However, it is not really easy to do that. So we can extend the dataset that we gathered with other related datasets that exist, the public ones. And as mentioned before, with the cat and dog example, what if there is a horse in the field of view? What do we do then? There are some methods to deal with it right now. So for example, you can have sample selections, or as I said, uncertainty. So you can have this metric that the network says, okay, this is a dog, but I'm not certain. So this is considered a sample selection. And there is a small problem with it, that usually you have the accuracy trade-off. When you want to get rid of uncertain samples, you sometimes get rid of certain samples as well, because the model is not perfect. The second way to deal with it is to have the open world, the open world recognition system. Whenever you see a new sample, you learn that sample as a new class, and you just begin building more and more classes, which quickly will turn into a hard problem with high computational cost, which is not desired in most cases. And then there is the potential of the adversarial attacks. Sometimes people deliberately want to make your system fail. It's not just like random images or random objects that you see, but people actually want you to fail. So how do we deal with those? Do we train for them? Pretty much all the papers that I have read so far, whenever there is a new way of dealing with adversarial attacks, 2 weeks later there is a new adversarial pattern that beats that method. So it's a little bit like funny to see that happening. There is no solid solution. It's, you can achieve a desired level of accuracy, uncertainty, robustness, whatever metric you're using, but there is no 100% for everything. You need to have a trade-off. Next step is the adequateness, or how your data is dependent or independent, and how they are equally distributed or not. So a simple solution would be just modifying model to accept any interdependent data, which has been proposed previously, and it works decently. So we don't have to deal with the dependency of the data as often. However, there are other solutions, like instead of labeling images with bounding boxes, which might overlap the objects together, we can do it pixel-wise to separate objects within a single frame of camera, to not have to deal with the overlapping at least. Or we can use stuff to, some stuff to enhance the performance, let's say. Other speakers already mentioned the knowledge transfer, or like domain transfer, which are pretty useful. You can learn with a clean, synthetic, simulated dataset and just transfer that knowledge with a few sample images on your real dataset. And more than that, you can have complementary data. It's not out of reach to use both LiDAR, camera, or any other sensors that you have to complete the problems, to overcompensate for the problems at least. Or you can have multiple tasks within the same dataset that might help your network. Like, let's say, a face detection already helps with the emotion detection. If you have a face detection methodology that works good, so you can just have both of them simultaneously work, and you get better results. However, there are problems still. How do we deal with small objects? As said, like Tesla is doing this with using different lenses, zooming further on to see the smaller objects. Is it the only way possible? So far, it seems so. And how do we deal specifically with the low representation of rare hazardous events? We don't know everything about our system, probably. If you're using AI, that is most of the times the case. You don't know what leads to the hazard all the times. And maybe your evaluation is not valid because you didn't even consider some cases. And we still need more research on this field as well. Sadly, we still need research on all the fields I'm going to talk about. This is rather a new field altogether. And as a last part, the size and the cleanness of the dataset are always hand to hand, because it's rather easy to gather a dataset that is small and clean. But as the size grows, the cost also grows, and people get tired of labeling and gathering good data, and it gets noisier and noisier. So how do we deal with this? Because noise is one part, but the cost is also another part. You don't want to spend millions and millions of dollars or euros to just gather one dataset for one task and just throw it away after the task is done. So there are some ways, as mentioned before, the simulated data or the augmented data can help with that. You gather one smaller set of dataset and then augment it, rotating, flipping the images, or even style transformations that are rather newer, which are really good to have. But there are some problems in the recent years. The noise is usually dependent on the instance, not on the generic all dataset, and we have to deal with them as well. And there is also cost of augmenting the dataset. The simulation and the synthesized data are not always close enough to the reality. And even with all these, if we have the perfect data, we have to choose the perfect model and the perfect hyperparameters, which requires expert knowledge, an expert that knows the machine learning and the field, which is hard to find, sadly. So we can automate this part by having a search algorithm. However, it costs to train a lot of networks on one dataset and just search which one is the better. So that is also our last problem in the training phase. Next, we come to the evaluation. Oh, okay, let's say we trained everything, and now we want to evaluate whether it's good or not. As mentioned before, AI scientists usually like to evaluate stuff with accuracy. However, accuracy is not of everything. We need to have different metrics based on what the task demands us. Maybe you don't care about detecting like traffic sign as much as you care about detecting a child. So a failure in detecting a child is much more costlier than a failure in detecting one traffic sign and just getting a, let's say, €500 of fine. So we need that as well, which requires expert knowledge and which requires careful thinking about how to deal with those, how to make a new cost function. And we don't have any benchmarks. So for every task, you need to create your own benchmark. Maybe you can share the benchmarks with other related tasks or other companies. But right now, we don't have anything for the industry, at least. We have a lot of stuff for, as said before, medical stuff or like autonomous cars, but not the industrial vehicles. Maybe the competitiveness of the task and the smaller scale of production is the issue here. And as a final part, I would like to address some of the stuff that others said. Petri mentioned there is a gap between the researchers and the industry. There is also a gap between these two parties and the legal entities. No one understands each other. So typically speaking, data scientists don't know anything about the safety concerns or what legal concerns are required for the safety. And on the legal side, there is no specifications. Like, do we need 2 meters safety, like distance from other cars? We don't know what we need. We have to define it ourselves. That is a big problem, and it has to be solved at some point. I don't know who is going to do it, but hopefully. And also there was this talk about from Sami that is AI safer than human? And I think no, AI is not going to be safer than human. Probably not soon enough, at least. But AI solves some problems that humans cannot solve on their own. So one way or another, we are going to use AI. So we have to make it as safe as required to make sure we can have those potentials, like as mentioned by Jussi, human detection. A human itself can do it really easily, but he gets tired. So if you want to automate the machine, you have to get into the AI part. It might not be as safe as a human driver, but it has a potential of removing all the labor from the humans. And then last, there was this point in like understanding the data by Kalle, which is that like the IMU data, you cannot even understand what it says to label it. How do we deal with that? From my research, I found several papers that mention some sort of how to make AI safe from safety engineers' perspective. And usually they mention these goals of make sure your data is good, which is too vague to be practical. Your data cannot be good. There is no practical way of making sure of that, because you have to either spend unlimited amount of budget and money, or you have to accept that your data is not good. So what I found out as a conclusion is that we actually need case-specific, or at least domain-specific standards that have these kind of practical issues targeted and answered. So we cannot deal with the generic like software standards and AI on the same side. And that's it, if you have any questions.